All right, let's go ahead and get started. Today we're going to be doing lecture 14, which is exponential and logarithmic equations. So we've been dealing with exponential equations and we've been dealing with logarithmic functions for a while. And the way we get logarithmic functions is by inverting an exponential function. So let's write this down. 2 to the third power equals what? Go ahead and try that on your own. 2 to the third power equals what? So I thought I'd start off today with this question because we're never really told what an exponential expression is. But an exponential expression is always going to have three things. It's always going to have the base, so the number that we're raising to the exponent, that's what we're calling the base. And then the power it's being raised to, the 3, is called the exponent. So the 3 is going to be called the exponent. And then the number over here, what we get when we take 2 to the third power, is going to be called the result. The result. All right, so what did you get when you did 2 to the third power? 2 to the third power, that's going to be 2 times 2 times 2. And that's going to give us 2 times 2, which is 4. We bring down the last 2. And then 4 times 2 is going to be equal to 8. So that was our answer. I'll go ahead and erase this and put down an 8. So 2 cubed, or 2 to the third power, is going to be equal to 8. Okay? So an exponential expression or an exponential equation is always going to have three things. There's going to be the base, which I'll put in blue. There's going to be the exponent, which I'll put in yellow up here. This is going to be b to the y power. And then on the other side of the equal sign, you're going to have what's called the result. And in this case, I'm going to put an x. So b is going to be the base, y is going to be the exponent that you're raising the base to, and x is going to be the result. This is called an exponential expression. Exponential expression. Okay, so this is an exponential expression, or since it has the equal signs, you can call it an equation. What we're going to do with this is we're going to rearrange some of the elements to make it into a logarithmic expression. So the way you do it is this. You're going to have the log, first of all. Log just stands for logarithm. Logarithm. And that logarithm is always going to have a base. In this case, it's going to be the base that we started off with, the b. So I'm going to put this b right below the g. And the base is just going to be a number, right? Okay. Then what we're going to do is we're going to have an expression in parentheses. We're going to have something in parentheses. And then on the other side, we're going to have an equal sign. All right, so what we're going to do with this is now we just need to know where to put the x and the y. Well, the y is the exponent. So what we're going to do with this is we're going to take the exponent, which is the y, and we're going to take it in our hand and we're going to throw it we're going to throw it over to the other side. So let me get my yellow, and I'll put the y on the other side because we just threw it to the other side, right? The exponent always gets thrown to the other side. And then the result that we get, that red X that you see, that result is always going to go inside the parentheses. And that's the last thing that I want you to think about. What's going inside the parentheses? That's going to be the result, not the exponent. Remember, we threw the exponent to the other side, right? So this is what's known as a logarithmic expression. Logarithmic expression. Okay. So B is going to be our base. B is going to be our base. Y is going to be our exponent. So I'll call this the exponent. And then the X is going to be our result. That's what we get when we raise the base to the exponent. Okay? So now, can we take that 2 cubed is equal to 8, and can we rewrite it as a logarithmic expression? We can. Go ahead and try that. We're going to take this expression right here, that 2 to the third power is equal to 8, and we're going to make it into a logarithm. Okay? So the first thing I do is I start off with the log. I'm always starting off with log, right? What is the base? The base is going to be that small number next to the g. Well, the base is 2, right? Because 2 is being raised to the third power, so 2 must be the base. I'll put the 2 right below the log. Okay. And now there's going to be a parentheses. There's going to be an equal sign. And what we're going to do is we're going to take the exponent and we're going to throw it. We're going to throw the exponent to the other side. So the exponent is 3. That's going to land the 3 right over here. And then the last number that we have left, the 8, that's going to go inside the parentheses. So the way you would say this is log base 2 of 8 is equal to 3. Okay? So this is really asking the question, what exponent do you need to raise 2 so that you can get to 8? What exponent do you have to raise 2 to make sure that you get to 8? And that's going to be the 3. So the exponent is always going to be on the other side when we're doing logarithms. And the result is going to show up inside the parentheses. Okay? So let's go ahead and try a few of these from the notes. All right. This first one is going to be 2 to the 5th power is equal to 32. And the second one we're going to do is going to be 3 to the 4th power. 3 to the 4th power is equal to 81. And what we're going to do with these two examples is we're going to make them change from exponential expressions to logarithmic expressions. So see if you can write these two expressions with logs. You're going to need the logarithm, right? So you're going to need to write down log. You're going to need to know the base. You're going to need to know the exponent and the result that you get once you raise that base to the exponent. Okay? So go ahead and try these two. Write them as logarithmic expressions, and then we'll go over them. I'll go ahead and start off with the log. We're going to write log for both of those. And we're going to start off with the base. So for the first one right here, our base is 2. So we're going to put a small 2 under there. The next thing we're going to do is we're going to take the exponent and throw it to the other side. So on the other side of the equal sign, you're going to have the 5. The exponent is 5, right? And then the result, the 32, that's what's going to go inside parentheses. So log base 2 of 32 is equal to 5. So this is basically saying, what power do I have to raise 2 to be so that I get 32? So I have to raise 2 to the 5th power to get 32. So my answer for that would be 5. Okay. Now go ahead and try number 2. See if you can write this one as a logarithmic expression. The first thing you're going to do is you're going to start off with the base. Then you're going to throw the exponent to the other side, right? The other side of the equal sign. And then inside the parentheses, you're going to have that result that you want. So for number 2, our base is going to be 3. We're going to have something inside parentheses. And on the other side, we're going to have the exponent that we threw over to the other side. So let's put a 4 right here. That's going to be our exponent. And then the last number is just going to go in the last place, right? So 81 is going to go inside the parentheses. And we're done. That's our log expression. Okay. Let's try a couple problems from the problem set. And we'll see how they work. Okay. From the problem set, we're going to be trying the odds. The even ones you can do on your own, right? All right. I've got 3 squared is equal to 9. And for number 3, I have 4 cubed is equal to 64. Okay, so go ahead and take those exponentials and make them into logarithms. And then for 5 and 7, we're going to be going the opposite way. We're going to be given a logarithm and we're going to change it into an exponential expression. So for number 5, we're going to have log base 2 of 128 is equal to 7. And for number 7, we're going to have a log base 3 of 81 is equal to 4. Okay. Let me group 1 and 3 together and 5 and 7 together. Okay. For the first problem, we're given 3 to the 2nd power is equal to 9. So I start off my logarithm. So what I want to do is I want to take the base and I want to use that first. My base is going to be 3 this time. And then what I'm going to do is I'm going to take the exponent and I'm going to throw it to the other side. So the 2 is going to get thrown to the other side. That's my exponent. And then the 9 that I get as my result is going to go inside the parentheses. So log base 3 of 9 is equal to 2. So that's basically asking the question, what exponent does 3 have to be raised to get 9? And that would have to be 2, right? Let's try number 3 together. Okay, so I'm going to start off with my logarithm. The first thing I look for is my base. That's the most important number. My base is going to be 4 this time. And then what I'm going to do is I'm going to take my exponent and I'm going to throw it to the other side. My exponent is 3. So the exponent is going to get thrown to the other side. And then the number that I have left inside my parentheses is going to be the result. That would be 64. So I put 64 in there and I'm done. Okay. So that's going from exponential to logarithm. Now what I want to do is I want to go the opposite way. I want to go from logarithm back to exponential. And I always keep my base in mind because that's the first number that I want to think about. All right, so I start off with my base. My base for this logarithm is going to be a 2. So I start off with that. Now I need my exponent because I threw it to the other side, remember? So I need that 7 to be my new exponent. That means that I'm raising 2 to the 7th power. And then what do I get on the other side? The last number that we consider, right? The 128. Let's try the next one. What's my base for number 7? What would my base be? This time it's a 3. So what I need to do now is I need to get my exponent. I threw it to the other side, right? So I'm going to take that 4 and I'm going to put that as the power over the space. And then what's the last number that I need to go on the other side? That's going to be my result, right? 3 to the 4th power. That's going to give me 3 times 3 times 3 times 3. That would be 9 times 9. That would be 81. So I put the 81 on the other side and I'm done. I got it. So you can go from exponential to logarithm, but you can also go the other way, right? You can go from logarithm back to exponential. Okay. Let's try some classwork problems. We're going to be trying the evens. Okay, so go ahead and try these two first. We've got 5 cubed is equal to 125. And we've got 4 to the 4th power is equal to 256. And what I want to do is I want to take these exponential equations and I want to make them into logarithmic equations. And then for 6 and 8, we're going to go the opposite way. We're going to be given a logarithmic expression, and we want to change it into an exponential expression. All right. So go ahead and take a minute and try those. We're going to do 2 and 4 first, and then we're going to go to 6 and 8. So I start off by writing a logarithm. But every logarithm has to have a base, or it wouldn't make any sense, right? You start off with the base, and then you do the exponent, and then the result is going to be the last thing that you think about. Okay, so let's go ahead and try number 2. We're going to have a logarithm, and what's the base for this going to be? It's going to be 5, right? I'm going to have something in parentheses, and I'm going to have something on the other side. That's going to be my exponent. In this case, the exponent is 3. So I throw that exponent to the other side, and then what am I left with? My result, 125. And I'm done. Let's try the next one. What's the base for number 4? It would be 4. Now, I'm raising 4 to some power. That's going to be my exponent. So that 4 that I just circled is going to get thrown to the other side. It's going to get thrown to the other side of the equal sign. And then my result, my 256, that's going to go inside the parentheses. Okay. So that's basically saying log base 4 of 256 is 4. It's saying what exponent does 4 have to be raised to get to 256? And it has to be raised to the 4th power for it to work. Okay, last 2. So this time I want to go from logarithm to an exponential expression. Let's go ahead and try 6. So what's my base for this logarithm? It's going to be 5, right? So I start off with the base, and then my exponent. I do that next. That's going to be the 2. And then 5 squared is equal to 25. That's going to be my result. Okay, let's look at number 8. Number 8, what is the base for number 8? The base is what? 4, right? So I start off with my base. Now I need the exponent from the other side. That's going to be 3. And then 4 cubed, that's 4 times 4 times 4. That's going to give me 16 times 4. That's going to give me 64. And I'm done. That's my exponential equation. Okay, so that's just a few of the classwork problems. I'm going to head on back to the notes. And what we're going to be doing now is we're going to be looking at exponential expressions and their counterparts, how they're related, and what are some special types of logarithms. Because there are some that are more special than others. And that's what we'll consider on the next slide. Okay. So let me start off with a note. Okay. The first thing I wanted to say is that logarithms are undone. I'll just use the word undone, but you'll know what I mean by the end of this. They are undone by exponential expressions. Exponential expressions. So what this means is if you ever have a logarithm and you want to get rid of it, you have to use exponential expressions. And the other way is true too. And vice versa. So the opposite is also true. If you start off with an exponential expression and you want to undo that, then you have to use a logarithm. And that's because logarithms and exponentials are opposites of each other. And what we're going to learn next week is that they are inverses of each other. So the inverse of a logarithm would be an exponential. The inverse of an exponential would be a logarithm. Okay. So what you're going to see is you're going to see that when you have a number, let's say it's A, we'll treat that as the base. And if we want to undo this exponential expression, what we need to do is we need to use a logarithm. So what you'll see is when you raise it to a logarithm power, you get back what's inside parentheses. So essentially what happened is when you have the base being raised to a logarithm with the same base, the two bases are actually going to cancel out. So let me switch over to red. What this means is if I have a base down below, let's say it's A, and then I have a logarithm with the same base, they're going to cancel each other out, and I'm going to be left with the X. And the opposite is also true. So you could have a logarithm with a base A, and if you try to take the logarithm of an exponential, like A to the X power, what's going to happen? They're going to undo themselves. You're going to be left with the exponent, which is X. So let me write that again over here. Okay, so same thing. I'm going to switch over to red just to show you that these two things kind of cancel each other out. So if you have a logarithm with a base of A, and you have an exponential expression, which also has a base of A, then the two bases are going to cancel each other out, and I'm only going to be left with the exponent. And I just bring that down. Okay? So that's going to help us when we get to equations a little later on. Logarithms are always going to be undone by exponential expressions, and then vice versa. Exponential expressions are always undone by logarithms. And that's because these two ideas are opposites of each other. So I'll write that down in a note. logarithmic functions, and exponential functions are inverses of each other. They're inverses. They're inverses of each other. Okay. You can think of them as inverses, or if you like to think of them as opposites, that's also true. So I'll leave that up there for a little bit, and then we'll move on to the two very special logarithms. Okay. So there are two special types of logarithms that you're going to see. They are called the common log. So let me divide up my paper. How about that? All right, so you're going to have the common logarithm. I'll put that on the left side. The common logarithm. And then on the other side, you have the natural logarithm, which is going to be the most important. We'll save that for last. So let's talk about these two very special types of logarithms. Now, the common logarithm is always going to have a base of 10. So I'll say always has base 10. Or b is equal to 10. So the way you would write that is log, and then the base would be under the g, right? So I would put a 10. Log base 10 of x is equal to y. That's going to be our common logarithm. So let's try a couple x values so you can get the hang of this. What is the logarithm base 10 of 100? What is the logarithm base 10 of 1,000? And we'll do 3 more. Logarithm base 10 of 10. Logarithm base 10 of 1. And logarithm base 10 of 0.1. So we're going to try all 5 of these. So remember, in a common logarithm, it's always going to have base 10. That's always going to be your base. So the first question is asking, if the base is 10, then what exponent do I need so that when I raise that to the exponent y, I get 100? Right? What base does 10 have to be? Well, what exponent does 10 have to be raised to get to 100? That would be 2, right? Because 10 to the second power, that's going to give me 100. So I'm going to erase this question mark and replace it with a 2. That's going to be my answer. Okay. So can you try the last four? What exponent do I have to raise 10 to get to 1,000? What about if I want to get to 10? And then how about 1 and 0.1? Right? What do those exponents have to be? So while you're doing that, I'll go ahead and erase these. And we'll go ahead and work on those together. Okay. So what exponent do I have to raise 10 to get to 1,000? Well, 1,000 is just another zero up from 100. So instead of 2, this time I'm going to have 3. So 10 to the third power is going to give me 1,000. Okay. What if I just wanted to get back to 10? What exponent do I have to raise 10 to just stay at 10? That exponent would have to be 1, right? Because 10 to the first power is going to give me 10. Okay. Well, if that's true, then what exponent do I have to raise 10 to get to 1? That's going to be 0, right? And that's because 10 to the 0 power is going to give me 1. And then the last one. Which exponent do I have to raise 10 to get to 0.1? Also known as 1/10, right? This time it would be less than 0. It would be a -1. So how does that work? Well, if you take 10 as your base and you raise it to the -1 power, what you can do is you can write that as a positive exponent in the denominator. So I'm going to have 1 over 10 to the first power, which is just 1 over 10, right? 0.1. So that's what I mean. Which exponent do I have to raise 10 to get to 0.1? And that would be the -1. So now you see how common logarithm works. We always have base 10. And if the base is not there, we always assume it to be 10. So we're going to say assume 10 if base not given. So that base number is so important, but when it's not there, like if we just have log x, so if I was to get rid of this 10 right here and we just had log x, since there's no base there, you would always assume it to be a 10. Kind of like how we assume there to be a 1 in front of that x and in front of that y, right? So there are things in math that we just assume to be true. And that would be one of those cases. If the base isn't given, you assume that it always has base 10. That's the common logarithm. Now let's look at the natural logarithm. This one's going to be a little bit different, and it's more complicated. The natural logarithm is always going to have a base of e. Always has a base of e. And e is going to be equal to 2.71828 ... That decimal goes on forever. Okay. E is irrational. It is irrational. So what does that mean? That means we can't write it as a fraction. So E is going to be this number that has a wild decimal expansion where we can't write it as a fraction. So that means it's irrational. it's always going to have that base of e. So that when we write the logarithm, we're going to write it as log base e of x is equal to y. So this is the logarithm that always has a base of e. Okay. So the base is going to be e. Why do we choose e? That's because it's the natural exponential number. And that becomes more and more important as you move on to pre-cal and calculus. But for right now, we can always write log base e as the natural logarithm. So the way I can rewrite this is I can say log base e is going to be ln. ln of x is equal to y, where ln stands for the natural logarithm. Okay. So whenever you're working with natural logarithm, you're going to assume there to be a base of e. Okay. That is natural logarithm. I'm sure there's more I can say about it, but due to time constraints, we're going to move on to equations. So I'll leave this up there for a little bit, and then on the next slide, we'll try some equations. All right, now when you do equations, what you want to do is you want to do the opposites. So if you see a logarithm, you're going to want to do an exponential. And the opposite is also true. If you see an exponential function, you want to use a logarithm to kind of neutralize it. So that way, those two functions will cancel each other out. So let's take a look at that. All right, we'll start at the notes. Let's try this one. Logarithm base 3 of x is equal to 5. And then on the other side, we'll do an exponential equation. 2 to the x power is equal to 16. Okay, so these two are equations. So I'm trying to solve for x. And when I solve an equation, I'm always going to end up with a number for my x if the answer does exist. And once I find the x, I need to put it in a solution set and then check it. But let's start off with the logarithm equation. So right here, what is our base going to be? Our base is going to be a 3, right? So when I do my exponential equation, I'm going to start off with a base of 3 and go from there. So let's use a base of 3. And I'm going to use a base of 3 on both sides. So I'm going to start off with a base of 3. That's the base for my logarithm. And then what I'm going to do is I'm going to treat both sides of the equation as the exponents. So what I'm going to do is I'm going to raise 3 to the power of the left side. And I get 3 to the logarithm base 3 of x power. And then on the right side, I'm going to take that 5 and make that into the new exponent. Okay. So now what happens on the left side? They cancel out, right? So I'm going to switch over to red. And these two bases right here, the 3 and the 3, they're going to get canceled out. So when I cancel those out, what am I left with? I'm only left with what's inside parentheses, the x. So I bring that down to my final answer. Okay. Now what's on the other side? This side is pretty simple compared to the last side. This is 3 to the 5th power. So that's going to be 3 times 3, 5 times. So 3 to the 5th power, that would be 81 times 3. Since I remember 3 to the 4th power is 81 anyways. And if I just multiply that by 3 again, I get 243. So that's going to be what's inside my solution set, the 243. Okay, so now I know what my answer is going to be. Now I want to check it. When I check this, I always start off with my original equation. My log base 3 of x is equal to 5. And what I'm going to do is I'm going to replace my x with the solution that I just got, the 243. So I get log base 3 of 243 is equal to 5. Okay. So now you're basically just asking yourself, what exponent do I have to raise 3 to get to 243? And that would be 5, right? So I get 5 is equal to 5. And that's my true statement. That's how I know that this 243 is actually going to work. Okay, so let's try the exponential equation. This time, we're not going to raise anything to a power because we've already got 2 to the raised power of x, right? So I'm not going to do that. Instead, what I'm going to do is, since I'm starting off with an exponential equation, what I'm going to do is I'm going to do the opposite. I'm going to do the logarithm of both sides. And you'll see how this works out. Because my base when I start off is 2. So that means when I do a logarithm of both sides, I need to have that base of 2 for everything to cancel out on the left side. So I'm going to take the logarithm base 2 of the left side. And I'm going to take the logarithm base 2 of the right side, 16. So all I'm doing is I'm taking the logarithm of both sides with respect to that base that we just found. Okay? And then what happens on the left side? The 2's are going to cancel each other out. So the log base 2 and the exponential base 2, they're gone. And then what am I left with? I'm left with the exponent of x. I have to bring that down. Okay. So what's the right side going to be in this case? Well, I have logarithm base 2 of 16. That's basically asking, hey, what exponent do I have to raise 2 to get to 16? And that's going to be 4. So my x is going to be equal to 4. That's my solution. So I write it in a solution set, and now I want to check my work. So when I check, I always start off with my original equation. And I just plug in my solution for x. This time it's a 4. So I get to raise 2 to the 4th power. and 2 to the 4th power is 16. So at the very end, I get that 16 is equal to 16, and that's my true statement. Okay. I'll leave that up there for a little bit. And then I want to move on to a couple more difficult problems that you may see on the problem set and the classwork. Okay. So on the next slide, we're going to do the exact same thing. We're going to do an equation on the left side and one on the right side. Okay. On this side, we're going to have log base 3 of x minus 2 is equal to 3. And then on the other side, we're going to have 4 raised to the x plus 1 power is equal to 16. We'll try both of these together. Okay. So for the first one, I have a logarithmic equation. What that means is I want to introduce an exponential expression so that we can cancel out the log and the exponential. That way I can bring the x minus 2 out. But before that, I have to choose the right base. And the base that they give us is a 3. So both sides are going to have a base of 3. What I'm going to do is I'm going to take that logarithmic expression and I'm going to make that the exponent. So on the left side, I have 3 raised to the log base 3 of x minus 2. And then on the other side, that 3 is going to become the new exponent. So on the right side, I have 3 to the 3rd power. So what does that do to the problem? What that does is it causes the bases on the left side to cancel out. So I have a 3 as the base. I have a 3 as the base of the logarithm. So what that means is whatever's left is going to come down, that x minus 2. On the other side, I have 3 cubed, which is 3 times 3 times 3. That's going to give me 27. And then the last thing I have to do is I need to get x by itself by adding 2 to both sides. So that way, that'll get rid of the minus 2. And then x will be by itself on the left side. So notice that the 2's cancel out because adding is going to be the opposite of subtracting, right? And I get 29 for my answer. So that's going to be my solution set. Okay, so when we check, what we want to do is we want to start off with our original, and we're going to replace x with a 29 and see what happens. So when I do that, I get 29 minus 2 on the inside. That's obviously going to be 27 if I subtract. And then I have a log base 3 of 27. What I can do is I can raise both sides with a base of 3. Or I could ask myself, what exponent does 3 have to be raised to get to 27? And that would just be a 3. So I get that 3 equals 3. That's my true statement. Let's work on the next one. This time I have 4 raised to the x plus 1 power. So I need to figure out what x is. Since I'm starting off with an exponential equation, I'm going to introduce a logarithm of both sides so that I can get rid of all the bases. So I'm going to take the log base 4 of both sides. Take the logarithm of both sides. So that way, on the left side, the bases will cancel out. So how does that happen? The log base 4 is going to cancel out with the exponential base 4. And I'm left with x plus 1 is equal to log base 4 of 16, whatever that is. Okay. So the last thing that I want to do is I want to subtract 1 from both sides. But before that, I'm going to figure out what log base 4 of 16 is. And that's basically asking the question, what exponent does 4 have to be raised to get to 16? That's got to be a 2, right? Because 4 squared is 16. So I'm going to get x plus 1 is equal to 2. And then I can subtract 1 from both sides. I feel a little bit better about doing that now. So now the 1's cancel out, and I'm left with x is equal to 2 minus 1, which is just going to be 1. Okay, so let's check it. I'm going to start off with my original equation. 4 to the x plus 1 power is equal to 16. So what I'm going to do is I'm going to replace x with the 1 that I just found and see how that works out. 1 plus 1 as my exponent is going to give me a 2. I get 4 squared is equal to 16, and that's going to give me 16 is equal to 16. That is my true statement. So that's how you solve the equations. What you really want to do is, before you do anything, you want to get the log by itself or the exponential expression by itself, and then you want to do the inverses. If it's a logarithm, you want to introduce an exponential expression. You want to raise them as the exponents of both sides. But if you're given an exponential equation, that's when it's a little bit easier. You can just take the logarithm of both sides. But just remember what your base is for all of these. Your base is going to be given to you in the problem. So you won't have to hunt and find that. It'll just already be given for you. And if it's a common logarithm, like going back a few slides, you know that the base is always going to be 10. But if you have a natural logarithm like ln, that's always going to have a base of e. So you know which base you need given what type of logarithm that they give you. Okay. So I'll leave that up there for a little bit. And then I'm going to spend the last 5 minutes going over some properties and what's going to be due on Sunday. Okay. Let me finish off the notes. So I'm going to move on to the next slide. And we'll talk about the 4 logarithm properties. Okay. Logarithm properties. These become very important the higher up you go in math. So for the logarithm properties, there are four main ones that you need to know. The first one is the product rule. The product rule states that if you have a logarithm of some base, let's just call it b, and you have the product of m times n on the inside, you can actually break up that product into a sum. And as you know, the sum, a sum is when you add, right? So you're going to have the expression broken up into log base b of m plus log base b of n. So that's the first property that you need to know about logarithms, the product rule. And then there is the quotient rule. That's the second one we're going to learn today. The quotient rule. So the quotient means we are doing what? Not multiplying, but dividing, right? So if we're dividing on the inside, then how are we going to break this up? Can you predict how we're going to do it? We're going to be using the same base, that's for sure. So we're going to have a base of b and a base of b over here. We're going to have m and n as the results inside the parentheses. But instead of a plus, we're going to use a minus. And some of you probably guessed that. So if you're dividing on the inside, you can change that to a subtraction if you break up the inside. And then there is the power rule. The power rule. So the power rule states that if you have a logarithm of base b and you're taking some number m and you're raising it to a power, let's just say it's x, then what you can do with that exponent is you can actually move that outside in front of the log. So that's going to be x times log base b of m. Notice where that x goes. It goes from the exponent to being on the outside. Now it's being multiplied by the log. So that's the power rule. And then the last one is change of base. So this will be the last one that I talk about. Change of base. Okay. So if you want to change the base, let's say you start off with a logarithm of base a and you want to change it to b, what you would do is you would just change that base and you would get a fraction. And I go over this on another video. So you're going to have x on top and you're going to have the old base b on the bottom. So that's going to be the change of base rule. So that's a way you can change from one base to another. All right. Okay, so you have two assignments. They are going to be the exponential and logarithm equations. And on Wednesday, we're going to talk about the functions. And then your third, it's really extra credit. I gave you a very tricky exponential equation. So see if you can do that, write up your proof, and then post it onto Canvas. And if you're right, I'll give you an extra 100 classwork grade. Okay? And that's it. Class dismissed. If you have any questions about today's lecture, or if you have any questions about the classwork or the problem sets, go ahead and throw those down into the chat box. I will be with you very soon. See everybody on Wednesday. Have a great day and make it a great mathematical day. All right. I'll see everybody on Wednesday.